In this video, we want to talk about how to find limit analytically, or in other words, we want to find limit without using numerical method or graphical method. So here is the theorem. That theorem actually is a very useful theorem when we find the limit analytically. That theorem says let C be a real number, fx equal to gx for all x not equal to c in an open interval containing c, if the limit of gx as x approaches c exists, then the limit of fx also exists, and their limits must be equal. Okay, so here that it sounds pretty easy. Here is if fx equal to gx. Most time when we get a function, the function is given as fx. But the question here is how are you going to find the gx there? It's easy to say it, but the question is how you find the gx. Okay, if you find a gx, why this limit actually equal? Just use an example. Use a graph to describe what's really going on there. For example, if you have a function like this here, okay, that's your function fx, and at one point, say x equal to 1, the function is not defined. That's a circle. Okay, this function is not defined. Okay, that's a circle. And also you have another function, which is exactly same graph, but this one is also at x equal to 1, actually is defined. So you can see for these two functions, they are exactly same except at x equal to 1, they are not same. The question here for this case we want to find limit x goes to 1 fx, and in this case limit x goes to 1 gx. Okay, this is a function of gx. This is a function of fx. So according to that theorem, basically says you can see these two functions exactly same, except at x equal to 1, this function is not defined, this function is defined. So then fx, even at x equal to 1, is not defined. So the limit actually exists, okay, exists and equals that function limit as x approach 1. Okay, so that's what we use this theorem to describe this here. Let's take a look at this example here. I want to find this limit. We know when we find a limit, the first thing we want to try is if I can do substitution. If I can directly substitute and x with 1 there. So you can see when you put 1 in there, 1 minus 1 is 0. 1 square, which is 1. 1 minus 1 is 0. So you can see that one you can't do substitution because that's 0 divided by 0. Okay, so what we can do, remember when x approaches 1 does not mean x actually equal to 1. So in other words, when x approaches 1, x minus 1 is not actually equal to 0. X squared minus 1 is not equal to 0, but it's very close to 0. Okay, for this function may have a limit when x approaches 1 there. Because what happened there, both numerator and denominator goes to 0, does not mean their ratio does not exist. The ratio may still exist. So how are we going to do it? So let's take a look here. We're going to rewrite this as limit x goes to 1. X squared minus 1. Use difference of two squares. It is x minus 1, x plus 1. X minus 1. Okay, so remember when x approaches 1, does not mean x equal to 1. Means that thing, although it goes to 0, but they are not equal to 0. They are not equal to 0. So if they are not equal to 0, means that's the common factor. We can reduce the common factor. So what we have here, we have limit x goes to 1, so x plus 1. So this x plus 1, if you call this is fx, so that one is the gx. So that's two functions will have same limit. That is according to our theorem. So basically, when you try to find a limit like this, you don't have to say, oh, I need to find a gx first before I do it. When you simplify, okay, reduce the common factor and the resulting function, which is the gx. If that function, the resulting function, the limit exists, that tells us the original function's limit exists. Because now is a polynomial, and limit, in order to find limit of a polynomial, all you need to do is just do substitution. Replace x by 1, so get 1 plus 1, which is 2. Okay, so that is the method according to that theorem. So with that, so here now we summarize what we want to use to find the limit. So here we have a strategy for finding limits. 1, learn to recognize which limits can be evaluated by direct substitution. Means whenever you have a function, you try to find limit. First thing you want to try is if I can do substitution. If you can means you can evaluate, get a fixed number. So that means you already find a limit. You don't need to do anything else. If you can direct do substitution and evaluate, the value exists. Okay, so which means you already find limit. What happens if you can't directly do substitution? If you do direct do substitution like this case, that's going to be 0 divided by 0. Okay, now it does not exist. And so then what are you going to do? If the limit of fx as x approaches number c cannot be evaluated by direct substitution, try to find a function g, agree with f for all x other than x equal to c. So that basically means number 2 and number 3 basically means you apply the theorem. Okay? When you apply that theorem means you need to do simplification. When you simplify it and you get the simplified function you call the gx, and to see if the gx limit exists or not. After you get a gx, see if you can do substitution. If you can, okay, then you find limit. If you still cannot, maybe you don't have limit. Okay, and the last step is use a graph or table to reinforce the conclusion. Means if you can use a graph to see, oh, that's roughly the graph does have limit, you can see it. Okay, then that basically say, okay, that's a confirm what your conclusion is. Okay, so let's take a look a couple more example. Let's take a look at first example. The first example we have here is a polynomial. Polynomial is always easy. When you find limit of a polynomial, all you need to do is just do substitution. Okay? And what you have here, okay, when you do substitution, you got negative x squared. So you replace all x by negative 2. So you have negative 2 squared plus 5 times negative 2 plus 6. Okay, I choose this example purposely. Okay, The reason is I just want to emphasize when you have a negative, okay, and parenthesis negative square, according to the order of operations, you have to do the exponential expression first. So which means you can't say, oh, can I do double negative give us positive? No, you cannot do that. You have to do the square first. So when you do the square, so negative 2 squared, which is 4, okay, you don't do the double negative give you positive 2, then you square it. You don't do that. That's violate the so-called order of operations. 5 times negative 2, that's negative 10, and plus 6. So rest, just go ahead, put them together. Negative 14 plus 6, this is negative 8. Okay, so that's as easy can't, but I still want to make sure you know this. Okay, follow the order of operation. Now, this is an example like what we did earlier. Okay, so let's try if we can substitution. If we can do substitution. Remember, the strategy says whenever you have function, first you want to try to do substitution. Obviously, that's case you can't. If you let x equals negative 3, that is 0. Negative 3 plus 3 equals 0. But don't say, oh, if that's 0, the limit does not exist. Maybe you need to check the numerator first. Also, so when you check the numerator, what happened there, you're going to have, see, negative 3 squared plus 5 times negative 3 plus 6. You have 9 minus 15 plus 6. You can see that's 0. So that tells us both numerator and denominator approach 0. Remember this, when you have a function involve fractions, if both numerator and denominator approach 0 when x approaches a number, so that means you may have limit. Don't just say, oh, both approach 0, no limit. You may have limit if both numerator and denominator approach 0. But if numerator does not approach 0, but denominator approaches 0, then you do not have limit. Okay, for example, if you do substitution, you find that you get 3 divided by 0. If you do substitution, you get something like this. That indicates you definitely do not have a limit. But if you have something like 0 divided by 0, you may have a limit. Okay, I won't say you do, but you may have limit. You may not have limit. We will see if you do or not. We have to do further, okay, and to check it out. Okay, so what do we have here? In this case, both numerator and denominator approach 0 like this. What do we try to do here? Because this is a polynomial, when you put a number equal to 0, that's equal to 0, that's equal to 0, so means you know the x negative 3 is 0. Make the numerator equal to 0. So you know x plus 3 must be a factor. You know x plus 3 must be a factor. So x plus 3 is factor. So you know x squared plus 5x plus 6 can be factored as x plus 3 times x plus something here. But that case is pretty easy to tell, which is x plus 2. Okay, and so now let me say one more time, because negative 3 make this equal to 0. So x plus 3 is a factor of this polynomial. So that's the reason I immediately write x plus 3. And with that, you know you can, in order to get this, so you can factor this, you get x plus 2. If you already know x plus 3, that's pretty easy to determine x plus 2. Okay, so now you can see x approach negative 3. This approach 3, negative 3 does not mean equal to. Does not equal to. So that's reason that thing you can still reduce. You can reduce this 2 factor. only leave x plus 2. So now you got the limit x goes to -3 x plus 2. So -3 plus 2, which is -1. Okay, so now you can see, and we follow the strategy there. Let's take a look. Next example here. This example, same thing here. I try to follow the strategy, try to do substitution. I immediately find I can't. Denominator equal to 0. But the good thing there is, if you do the substitution, you find numerator going to be 1/4 minus 1/4. That's also approach 0. So that means that is like a 0 divided by 0 form. From here, you cannot say you don't have limit. You may have limit. As I mentioned, if the numerator does not go to 0, denominator goes to 0, then you don't have limit. But for this case, you got 0 divided by 0. So you may have limit. So you can see for this case, the problem caused by x goes to 0. So now you want to do here, you got to think how I'm going to get rid of this x if I have a limit. So means somehow from a numerator, you definitely will get a factor of x. So then you can reduce the x with the denominator. So then you can have limit. So how I'm going to do it, okay? So what do you try to do here? I need combine this fraction first. I just go ahead and do that fraction first, okay? So 1/x plus 4 minus 1/4. So that equal to the common denominator is 4 times x plus 4. 4 times x plus 4. And that one, if you get x plus 4 times x plus 4, obviously you need a times 4 here, you need a times 4 here. So the numerator becomes 4. Okay, that's the first fraction. The second fraction you have here, and you need a times x plus 4 here, you need a times x plus 4 to the numerator. So you're going to have x plus 4 and 4 times x plus 4. So now you can see I have 4 times x plus 4, and the numerator is 4 minus x. Look here, minus the whole thing here initially. So here, minus that's the whole thing here. Then you need to put a parenthesis here. And then you can see here I have 4 times x plus 4. When I drop the parenthesis, I'm going to change the sign to every term. So 4 minus 4 canceled. I get a negative x and 4 times x plus 4. Okay, so the numerator, after I combine together, I got this, which does give you a factor of x. Okay, so now I'm going to rewrite the whole thing here. I write this limit x approaches 0. The numerator is negative x divided by 4 times x plus 4 divided by x. So now divide by x is same as multiply its reciprocal. So now this x and this x reduced. It turns out you have limit x goes to 0 and -1, -1, -1, 4 times x plus 4. So now you see here, now if I do substitution, everything's fine. You're going to have -1, 4 times 0 plus 4, so which give us -1/16. Okay, so that's how we do it. Okay, so here the key point is this. When you combine those two together, you should put a parenthesis. You say, I don't want to put a parenthesis. Then you should change the sign to every term. That's the key. Most time people can get this part but forget to change the sign, and so then you get it wrong there. Okay, so let's take a look at the last problem. Okay, we have here, again, I do substitution first. 0 definitely doesn't work. But the numerator, if I put a 0 there, you got square root of 1, which is 1, minus 1, which is 0. So that is 0 divided by 0. So now you may have a limit. Okay, you may have limit. So now the question here, how am I going to get the limit? Because the numerator, obviously I cannot get a factor of x to reduce with this x. So what we try to do here, that is this method. When we do this here, we try to do something called rationalize the numerator. Rationalize the numerator. Rationalize the numerator means I want to get rid of the square root. But someone going to say, oh, can I just square them? No, you can't square. That's fine. You cannot square them. If you square them, you change the problem. Say if that's the answer is supposed to be equal to 2. If you squared, you got 4. Obviously, you cannot do that. But when we, so how are we going to, okay, rationalize the numerator? Rationalize the numerator means I need multiply the numerator and the denominator by the numerator's conjugate. The conjugate is x plus 1 plus 1. Okay, what do we mean conjugate? Suppose you have a minus b is an expression. Then its conjugate is a plus b. Vice versa. A plus b's conjugate is a minus b. A minus b's conjugate is a plus b. So all you need just change the sign of this. Here you have this. So you multiply the conjugate to the numerator, also to the denominator. And that does not change the function value because this, if you reduce, that's back to the same function there. But the good thing there is when you have a conjugate multiply, so it means you have a minus b times a plus b, you will find according to the difference of two squares, all you say do the FOIL. You will find this is a square minus b square. Okay, that's a minus b times a plus b is a square minus b square. So for this case means our a is this, b is 1, a and b. So here, if you multiply that's 2 together, which really is a square minus b squared, which is x plus 1 squared minus 1 squared. Okay, that is all. If you just go ahead and do the FOIL, you will find that you're going to have this. Denominator. Okay, here, that's the key. Denominator. Don't do anything to the denominator because the reason you do this, you rationalize, you hope you can get a factor of x to reduce the x with the denominator. Okay, if you distribute the x to each of them, then the factor is gone. You cannot reduce the x there. Okay, so then definitely that's going to be wrong if you continue to do the substitution there. Okay, so make sure don't do the distribution. So now you have x approaches 0, x plus 1 square root, and that square which is x plus 1, and minus 1 square which is 1. So 1 minus 1 cancels out. X, although that's x approaches 0, but it's not equal to 0. So those two common factors are not equal to 0, but approach 0. You can reduce them. So it turns out you're going to have limit x approaches 0. The numerator is 1, denominator is x plus 1 plus 1. A square root of x plus 1 plus 1. So finally, you can do substitution. You have 1 over square root 0 plus 1 plus 1. So square root 1, which is 1. Okay, you got 1/2. So now you have limit. Okay, so this is rationalize the numerator. If this is in the denominator, that's in the numerator, then you rationalize the denominator. For example, if you function like this, you're going to do exactly same what we did here. You just rationalize the denominator. So hopefully, you can get rid of the common factor x there. So you can try that problem. Okay.